Okay, thanks for the introduction. Good morning, everyone. So I want to introduce you with the development of my doctoral thesis that is entitled Model Predictive Control Applied to Turbulent Flows. So as it is already clear from the title, the focus of the thesis is exactly the one of developing flow control strategies, where controlling a flow means exactly the ability to manipulate a flow in order to achieve a specific target. So in order to make a more practical example, let's see at this image. So you see there is an airfoil. It is in a condition of high angle of attack. Probably it's describing a condition of an aircraft during the approach phase to the airport, probably a landing. What they do, the authors, in this, in order to control the flow, they just put some specific actuators on the surface of the airfoil to delay the separation. So you see that actually at the beginning of the video, the flow is separated from the beginning of the airfoil. Of course, flow control can be used also for more targets, like a list of them. It's represented in the slide. Just to name one of them, it's drag reduction. It's really important for for example, the reduction of the pollutant dispersion. But flow control can be used for different aims, let's say, but also in many different strategies. The more, let's say, powerful is the one of active flow control. That means that we have sensors and actuators. The sensors are informing us about the state of the flow at each during the time, while the actuators are exactly the devices that we use to manipulate the flow. So we need power of actuation to activate both of them, but most importantly, we need an algorithm that is a control strategy that is mapping or telling us how to perform the decision-making process. Well, among the active flow control strategy that my thesis is focused on the one that is called model predictive control. When it comes to explain what model predictive control does, I really like performing the example with the comparison with the game of chess. So when you play chess, generally what you do is to try to predict as much as possible the steps of the game into the future. Of course, you use a model of the opponent. The model that you have of the opponent is imprecise, so you cannot use it until the end of the game. So you focus just on the first 3-4 steps of the game. You perform an optimization on the movement, so you have at the end of this optimization, based on the prediction, an optimal control strategy. And at the end of this optimization, you just make a single movement because you are allowed to do only one single movement. So this is how exactly model predictive control works in, let's say, in a simplistic way. This is not something really artificial, so we find it also in nature. If you observe like how the dragonfly perform their, let's say, prey capturing their hunting, what they do is that they have internal models, like based on the impulses that they train with the experience, in order to predict the movement in order to anticipate the movement of the prey and capture them in a really efficient way. So, and this is represented in the video here. Well, if I have to explain it in a more, say, technical way, so what we have is we have a plant. This is the system we want to control, so the fluid flows. This is represented by a state. We want to make the system state, so the state exactly of the fluid, to follow a specific target. Let's, for example, think about drag reduction, lift stabilization, lift enhancement, or whatever it is. And in doing so, you have to select an input at each time step of the control. This is done here by the control optimizer. And in doing so, you can also use the information from a partial or total measurement of the state. So what is happening inside the control optimizer is exactly that you start from an initial condition. You use a model of the system. So you have a model of the reality, a model of how the flows behave. And you use it to perform prediction in a prediction window. Of course, the prediction window is limited because you have also limited prediction capabilities. So you start doing open loop prediction under a sequence of control action. You optimize this, you build a cost function depending on your target based on this prediction. You optimize it. You can also include constraints in this optimization problem. And after you have the optimal control strategy, you just select a first initial step, and then you repeat the process at the next iteration. So what the challenges in doing so? So first of all, we need a model of the plant. And this is particularly challenging for fluid flows because of some characteristics of the fluid flows. They are multidimensional, chaotic, nonlinear, multi-scale in space and time, and you also have time delays. You really need to perform model order reduction techniques. You have to reduce the space of your model, of your system, but in doing so, you're also losing accuracy. So it's a matter of making a trade-off between accuracy and computational cost, because remember that MPC has to perform an optimization on the fly. So this is a timeline of the activities I have been carried out during my PhD. So the first year was mainly like used for literature review process, especially about MPC, nonlinear system identification strategies. I started applying the MPC on a simple laminar chaotic 2D problem, like the fluidic pinball, and explaining it in a moment. And this ended up in a first publication in the Journal of Fluid Mechanics about the control on the fluidic pinball. So fluidic pinball is exactly a cluster of 3 cylinders. And it's a perfect example of multiple input, multiple output flow control with many actuation mechanisms and a rich dynamics. And the control goal here was to control the forces, so the drag minimization and the lift oscillation suppression, like lift stabilization. And the control actuation was exactly tuning the rotational speed of the cylinders. So here you can find a schematic of the algorithm. So you have in the main part, in the model predictive control, you build a cost function. The model here was based on forces of the fluid pinball, so exactly drag and lift, and was obtained by a technique that's called SINDI, sparse identification of nonlinear dynamics. And since we wanted also to test this in experiment, we also included some noise in the sensors and a statistical technique called local polynomial regression for data smoothing, for noise smoothing. But the story that we wanted to tell with this paper is that when you really go into the application of MPC for fluid flows, you never have one single target to optimize. You have multi-objectives, and you have to define one single cost function. So it's really important that this MPC depends on some hyperparameters, like, for example, the relative importance you give to the different targets you have specified inside this cost function. And if you select these parameters by hand, of course, you end up in a suboptimal solution. So that's why we included an external optimization loop with Bayesian optimization to perform this hyperparameter selection. Just to convince you, this is what we have. This is the drag, the lift, and the actuation, the rotation of the 3 cylinders. This is what you have is if you select by hand these parameters, giving the same importance to drag and lift control. And these are the results if you do this selection automatically by Bayesian optimization. Here there is another example. Of course, this is characterized by poor performance, while here you do it pretty good. This is another additional example in which you, instead of minimizing the lift oscillation, you perform a trajectory tracking around a set point that is a sinusoidal function. So, well, this was the first part of my PhD. I then also focused on an experimental validation of this. I'm not talking about this because this will be the main focus of Alicia's thesis, so stay tuned for the next presentation. And in the meantime, I was also focusing on another important aspect of MPC. As I was telling you, it's the importance of having reduced order models for to be optimized from MPC online. So that's why we investigated a technique that is called isomap. This a manifold learning technique that is able to, in this case, discover a low-dimensional space in which the data actually relies, because there are coherent structure in the data we are observing, like data, I mean, snapshot of fluid flows. And we were able also to perform, like an estimation process starting from this low-dimensional manifold. Of course, if you have coordinates describing the low-dimensional manifold that can be also interpretable, these are really important for the design of control strategies. This was just studying the post-transient solution of fluid flows due to steady actuation. So the part of unsteady actuation still will be the main focus of Alicia's thesis. So after this, I completed a research stay in France with Professor Onofrio Semeraro and Lionel Matlen. I spent there in the CNRS, the LIS laboratory, 3 months there discussing about how to embed and merge the model predictive control capabilities with another semi-supervised learning control strategy, this the reinforcement learning. So in particular here, what we are still investigating, I hope the results will be published soon, before the end of the PhD. And so here is exactly use the control authority of MPC to guide the process of learning a secondary policy, that is a student policy, that is performing a direct mapping between observation states. We wanted to do it in a safe manner because reinforcement learning needs exploration, so you have to make a lot of errors before getting an optimal policy, while MPC, as I told you, is able to include constraints in the optimization, so you can run safe control in this case. And we want to not only do safe control, safe learning, but also safe control. So this is the scope of the current research we are focusing on now. And of course, learning a policy will be helpful also for having a control that is more scalable to more complex systems or lab scale environment, let's say. Well, after that, hopefully an experimental validation of all the methodologies developed during the thesis. And here it is a list of conferences and the journal publication. I would just want to name another one that we did externally about, in collaboration with some professors and PhD students from the Arvin Institute of Technology, about the estimation of fluid flows around unmanned aerial vertical vertiport. So this is also a list of courses attending and dissemination activities. That's all from my side, and I would be very happy to receive some questions. Thank you.